Okay, I'm going to try another weak base being titrated with a strong acid, simply because the previous one we had way more strong acid than we did weak base, and we ended up with just strong acid at the end. And then it was just the matter of taking the negative log of the H plus concentration, and the problem was actually really straightforward. In this case here, we again have a weak base, and if you're looking at H3 and going, how do I know it's a weak base? Well, a couple things here. One, they give you the pKb of it. That means it's a base. And then two, we are titrating it with HNO3, which is a strong acid. Now, a gentle reminder that every single titration, we do two problems. Number one, do the stoich. In other words, we are going to write an equation of the acid reacting with the base, and it's going to be done in millimoles. It can also be done in moles, but we don't want to have to convert from milliliters. That's step one. Step number two is after we've taken care of this HNO3 that we're adding in, we're then going to do the equilibrium. Now, what's important about the equilibrium thing is you can either do an ice problem or you can do the Henderson-Hasselbalch equation. Or if, like in the previous case, if the HNO3 runs over everything, you can just do the equilibrium value of the strong acid. But in this case right now, let's just see where it leads us. And so the number one thing we have to do here is to write an equation out. Now, they're giving us an HNO3, and really HNO3, isn't it, since it's a strong acid, doesn't the NO3, doesn't it pretty much completely dissociate off, and don't we just have H plus? So sometimes what they'll do, though, is they'll write HNO3 on one side, and on the other side, they'll write NO3 minus, knowing that we've accounted for the NO3 on both sides, and that reacts. But I would suggest just writing the H plus reacting with this, because that leaves you less chance to make a mistake. So we're just going to write here our stoichiometry equation. So we're going to do the stoich first. So we're going to write NH3, which is our weak base, and we're going to react that with H plus, and it's going to form NH4 plus. We're going to get really used to the fact that they love using ammonia because it looks like it has a bunch of hydrogens and could be an acid, but really it's a base. So our first step, always when we're dealing with problems, is we're going to rearrange the molarity equals moles over volume equation to be molarity times volume equals moles, because remember what we need to do here is we need to figure out the millimoles of this and the millimoles of this, because they're going to react, both of these, until one of them is used up. So I also call this an ICF problem. I know that's probably not good form, but that's initial, change, and final. But I'm going to figure out first the moles of my ammonium. So if I take a look right here, I have 103.3 milliliters, and I have 0.4900 molar. So let's plug it into our equation right here, and we're going to end up with 0.4900 molar, and that's all going to be multiplied by 103.3 milliliters. And when we solve that, that's going to give us our millimoles. And in this case right here, it's going to be 50.617 millimoles. Now, this is for the NH3, so we're going to go 50.617. I'm not going to write the millimoles in here at the moment. And then we're going to have to do, this is for our NH3. Now we're going to have to do the same exact thing for our H plus, our molarity times volume equals moles. And this time when we look at it, they give us 36.4 milliliters, and they give us a 0.6300 molar solution. So those are the two things we're going to be multiplying over here. We're going to write 0.6300 molar. We're going to multiply that by the volume of 36.4 milliliters. And when we multiply those two out, we end up with 22.932 millimoles. So over here we have 22.932. Now we're starting off with 0 of this. Now, since both of these right now, it's a fight to the death. Either H plus or NH3 plus, or NH3 is going to get used up completely. It just so happens we have way less H plus than we do NH3, so the weak base is going to survive this, and what's going to happen is we're going to lose all of the acid, that whatever we're titrating with right here, we're going to lose all of it here, and we're going to subtract this over here, and we're going to add it over here. Because remember, this is part of our overall equation. Now, when we do the subtraction here, we're going to end up with 27.685 millimoles of this, and 22.932 millimoles of this. And we love this so much because we have NH3 and we have NH4+. And anytime we have an acid and a conjugate base, we can use the Henderson-Hasselbalch equation, which we are very excited to do. Now, before we do that, we need to convert this to molarity. Now, I would suggest doing this so you don't have to do the math more than one time. I would take the two volumes and put them underneath here, 103.3 milliliters plus 36.4 milliliters. And we're going to do that again over here, 103.3 milliliters plus 36.4 milliliters. And what's cool about this is that when we go to put it into our Henderson-Hasselbalch equation, remember our Henderson-Hasselbalch equation is pH is equal to the pKa plus the log of our base, with our base over our acid. Now, you may have been wondering here, when they gave us this problem, they initially started off and they gave us the pKb of 4.74. Well, in order to figure out the pKa, we know that Ka plus Kb equals 10 to the negative 14. So if we take pKa plus pKb, that's going to be equal to 14. So I'm just going to move this over to the side here a little bit. So we have that. If we do the subtraction here between these two, they gave us the pKb, and they gave us our pKa is going to be equal to 9.26 because we put the 4.74 in right here. So our pKa over here is going to be 9.29. And this is what's really, really cool. We can take the log and we can take this entire thing right here and we can put it on the top. And we can take this entire thing right here and we can put it on the bottom. And because I have the ability to do this and I don't want to write it more than once, I'm going to take this and put it right here. I don't want to have lost this part right here, so I'm going to bring that back up here, wherever that was. I have no idea. This is going to go on the top. And all of that is going to be divided by, and I'm going to again write all of this and bring it down here. And remember that this log right here, this is the logarithm of this entire thing. And the reason this is super cool, and the reason that we didn't bother to do the math originally with this right here, is that if you take a look, isn't this right here and this right here, aren't they the same thing? So we can actually just cancel them out. This cancels out with this. So then when we're doing our math, all we're doing is we're taking the 9.29 and we're adding that to the log of 22.932 all divided by 27.685. And that ratio is going to give us log here of 0.0818, which we're going to add to the 9.29. And when we do that, there's a whole bunch of more numbers on this, 8182183. When we do that, we're going to end up with 9.341821. And they, as always, they ask us to do it to two significant figures. So that's the two significant figures right here. So our final answer for our pH is going to be equal to 9.34. Now let's just verify and see whether or not in the original problem, whether or not we would have used only two significant figures. And right off the bat, we have four significant figures here, four significant figures here, four significant figures here, and three significant figures here. So our answer should have had three significant figures. So we would have made the cutoff right here and called it 9.342. So anyway, we love it anytime that we have a problem and after the big dog has been taken care of, if we have both the base and its conjugate acid or acid and conjugate base, and it doesn't matter which one we have first, we can use this equation always. Now, if they give us a pKb, we might have to convert to pKa. But this is what I would suggest you do every time we have a problem like this. Hopefully this has been helpful.